point of confusion in kinematics is the meaning of the plus and minus signs for velocity and especially for acceleration. We can look at several ways to consider the meaning of these plus and minus signs. The first thing we'll look at is car, because most of you have some experience in driving a car. If you put the car in drive, it will obviously move forward, and we will call that a positive velocity. Put the car in reverse, it will back up, and we'll call that a negative velocity. Now consider what happens if the driver's foot is on the gas. The car will obviously be speeding up. But our problem is how to interpret the car's acceleration. As we will see, a positive acceleration does not necessarily mean speeding up, nor does a negative acceleration necessarily mean slowing down. How we interpret acceleration will depend on what the car is doing, whether it is in drive or whether it is in reverse. We need to do that to be mathematically consistent with our definitions for velocity and acceleration. Recall that acceleration depends on how the velocity is changing. And the velocity, not the speed, includes plus and minus signs. So let's consider the car in drive while the driver's foot is on the gas. The car's velocity will get more positive and numerically larger, or, if you will, farther to the right on a number line. This will make the acceleration positive. But if the car is in reverse, the velocity will get more negative and will become numerically smaller, or farther to the left on a number line. The acceleration will be negative. Recall that negative 20 is numerically smaller than negative 10. Likewise, if the driver's foot is on the brake, the car will obviously be slowing down. How this affects the acceleration will depend on whether the car is in drive or in reverse. In drive, the foot on the brake will result in a negative acceleration because the velocity will be getting numerically smaller. But in reverse, the velocity actually becomes larger, or if you will, becomes less negative. And less negative is in a sense a double negative, and that yields a positive acceleration. If this explanation doesn't click, then hold on, we're going to consider other examples that may help clarify it. But also consider what happens if the car is in park. Well, then obviously it will be in rest and the velocity will be zero. But if the velocity is zero, must the acceleration also be zero? And the answer is no. It may, but it doesn't have to be. If the car remains in park, then the velocity remains zero and doesn't change, and it is this lack of change that will make the acceleration to be zero. But put the car in drive and the velocity will not remain zero, and the acceleration will not be zero because the velocity will change. It will become positive. So for a split second, we will have a car with zero velocity, but it won't remain zero. It will be accelerating, and the acceleration will be positive. But the car in reverse and the velocity again will change, and the acceleration will not be zero. But now because the velocity will go negative, the acceleration will be a negative change, and that will be a negative acceleration. So again, for an instant, the car will have a zero velocity and negative acceleration. But note, there's nothing really special about a velocity of zero. One can say the exact same thing if the velocity happened to be 3 meters per second. It can only have a velocity of 3 meters per second while having a positive acceleration for a split second, because an instant later, it'll be moving faster and will no longer be moving 3 meters per second. Now let's consider another example. Let's consider the problem graphically. And here we're going to consider a velocity time graph where the slope of the graph will be the acceleration. The graph we have shown right here has a constant negative slope. So everywhere on this graph, the slope is negative and the acceleration is negative. Where the velocity is positive and the acceleration is negative, that will mean the velocity will be getting smaller and you'll be moving down towards the horizontal time axis. Down here, where the velocity is negative and the acceleration is negative, the velocity is getting smaller, but in this case, smaller means more negative. And in a sense, it is speeding up, but it's speeding up going in the negative direction or backwards. Right here, where the line crosses the axis, notice nothing happens to the slope. The slope remains negative. In fact, it remains the exact same value it is all along the graph. So for this one split second right here, we will have the car at rest, but accelerating in the negative direction. Consider another graph where we have a positive line the entire way. And again, everywhere the slope is positive, everywhere the acceleration is positive. Over here, where the velocity is positive, we'll see the car speeding up, moving faster and faster. Down here, it will also be moving with an increasing velocity, although its speed will be decreasing, because the speed will go from minus 20 to minus 15 to minus 10 to minus 5. But all of those are numerically larger values for the velocity, so the acceleration will be positive. And again, nothing special happens when you cross the axis. Where the velocity is 0, the slope is still positive, so we still have an acceleration even when you pass through the origin. One way to consider speeding up and slowing down on this graph is speeding up means you're moving farther away from the time axis. If you're slowing down, you're moving towards the time axis. But that's unconnected to the slope of the graph. So we should not be interpreting the slope of the graph to be speeding up or slowing down. Now we can consider some numbers. And since the confusing points usually are when you're in reverse, let's consider calculating the acceleration when you're speeding up in reverse. We'll take an example. Your initial velocity is 5 meters per second, but it's backwards, so we'll slap a minus sign to indicate the direction. Your final velocity is faster at 10 meters per second, but it's still backwards, so it still has a negative sign in front. And we'll say this change in velocity takes 1 second. The change that we use to calculate acceleration is always the final value minus the initial value. Final value is minus 10. We subtract a minus 5, and that gives us a total change of minus 5 meters per second. And that takes 1 second. Our acceleration will be negative, minus 5 meters per second per second. Now consider slowing down while in reverse. Now we'll be moving at a slower rate from 10 meters per second down to 5 meters per second. But we're still moving backwards, so we still have to slap the minus sign to indicate the velocity is backwards. And again, the change is final minus initial. The final is now the minus 5. We have to subtract the minus 10, which is the initial. And when you subtract a negative number, that's the same as adding a positive. So our change in velocity is plus 5 meters per second. We went from a larger negative number to a smaller negative number, and that is a positive change. That will give us a positive acceleration, just as we saw before. The last way we can consider this is by just drawing the velocity and the acceleration vectors. If the velocity and the acceleration vectors are both in the same direction, then we'll have the object speeding up. If they're in opposite directions, then they'll be slowing down, because this acceleration will be added to that velocity and it'll make it smaller. And here, this vector is going in the opposite direction as the acceleration. So again, when we add a small change of velocity, it will make this vector smaller. But note, when we have a positive acceleration, which is what we have here and what we have here, we do not necessarily have it speeding up. It's how the velocity and the acceleration vectors are oriented relative to each other that determines speeding up and slowing down. So what we've looked at are basically 4 different ways to answer the question, what do plus and minus signs mean? First was with a concrete example using a car. The second was considering some graphs, particularly velocity time graphs. Then we did a numerical example. And then right here we have vectors.